talk about an angled projectile. Now, let's first start by drawing a vector to represent an object shot at some velocity v, and we're going to shoot it at some angle that we will call theta. Now, the reason why we call these angled projectiles is because they're being shot at an angle, so we're not shooting them horizontally anymore. What that means is that the velocity that is given to us, because remember, often what we're given in these problems is that initial velocity. Well, that initial velocity is no longer just in the x direction like it was before. Instead, there is certainly a component of it that is in the x direction, but there is also a component of this velocity that is in the y direction. So before we start the problem, we're going to need to calculate the amount of the initial velocity that is in the x direction and the amount of the initial velocity that is in the y direction. In order to calculate this Vx and Vy, the only things that you need to know are the total initial velocity, which we called v, and then the angle that you're shooting at, theta. So if we were to find the x velocity, we could do that by using our knowledge of trigonometry, which boils down to Vi cosine of theta. And I guess we can add some i's to all this stuff to remind us that this is really an initial velocity we're talking about. Initial velocity in the y direction, again, we're using our knowledge of triangles, which boils down to the fact that the y component will be Vi sine of theta. So inclined projectiles use the exact same equations and the exact same problem-solving process as what we've been using for this unit so far. The only thing that changes is that you have to calculate that Vx, you have to calculate that Viy. Now, let's talk about some patterns that we can get from inclined projectiles. So let's look at perhaps what happens when we shoot a projectile at some angle from the ground and then it lands right back on the ground. Now, it doesn't have to be exactly ground to ground, but what we're really looking for here is the fact that the height that you shoot it at is the same as the height that we land at. And if the height we shoot it at is the same as the height that we land at, well, that tells us that our total delta y is 0 meters. It also means that we have the most symmetric shape that we could possibly have, right? Our peak occurs right in the center. So that tells us a couple other things. It tells us that the time to get to the peak, since it's right in the center, that must be 1/2 of the total time. If we look at this shape right now, if we look at where this peak is occurring, the range of that peak, so where it happens in the x direction, is 1/2 of the total range of the projectile. Total. These are really interesting things for us to know because we can use this knowledge to our advantage as we solve problems. And we'll solve some problems in the next video lecture. But before we get to that next video lecture where we solve other problems, let's talk about other situations where we can have angled projectiles. We may have an angled projectile that starts very, very low, and we shoot it, and it lands higher than where it started. And I mean, this could go the other way as well. We could start very high, we shoot that projectile, and then it lands much lower than where it started. There are different patterns that apply to these two situations. Number one, we actually do have some kind of a delta y, okay? So our delta y is no longer 0. It is some non-zero number. Now, it could be a positive delta y, like in our first example, because we are landing higher than where we started. Or it could be a negative delta y, like in the second example, because we're landing below where we started. And to signify that up or that down, we need to use a positive sign or a negative sign. Now, if you notice where these peaks are, the peak of the motion is no longer right in the center. it's skewed to one side. So that tells us that the time it takes to get to the peak is no longer going to be half of our total time. The time to get to the peak could be in the first half of the motion, it could be in the second half of the motion. Same thing with where that peak occurs. Where that peak occurs is skewed, so it is no longer right in the middle of the total motion. That's something for us to keep in mind. Now, I can tell you right now, this is a big problem-solving hint for angled projectiles where the launch height and land height are different. If you have a problem where it is an angled projectile and the launch height and land height are different, you must solve a quadratic equation. Oh yes, quadratic equations. You remember that from math class. You thought they were totally useless and that you'd never need to use them in the real world? This is where we need to use it. But you must solve a quadratic equation to find the time in the air. There's no getting around it, okay? I've seen students try to do it. They try to do some fancy algebra so that they don't have to solve a quadratic equation, and it does not work. It fails every time. If you are starting and landing at different heights, you have to solve a quadratic equation to find time. All right? Now let's click on the next video so we can solve some practice problems.